Okay, let's talk about a piece of cutting-edge technology, a brand new business jet prototype.
Right.
This is really the culmination of years of design work, huge investment, built for incredible speed, capability.
Top of the line.
And it's time for that critical phase.
Yeah.
Flight testing. This is where they push the limits, rigorously testing everything to make sure the production aircraft will be safe for everyone.
Absolutely crucial stage.
But imagine this. During one of the very first test flights for this sophisticated plane, it crashes right after lifting off the runway.
Yeah.
This happened on April 2nd, 2011 at the airport in Roswell, New Mexico.
Yeah.
And all 4 highly experienced test pilots and engineers on board died.
It's just a shocking event, isn't it? Especially given, the caliber of the aircraft, the crew involved. Flight testing always carries risk, sure, but a crash like this so early in the program, it really suggests the underlying issues might be deeper than just some test anomaly.
Absolutely. This wasn't some mid-air emergency. It happened right there, basically at the start of its flight life. So our mission in this deep dive is to take the source material you've shared and really pull apart the intricate, kind of multi-layered story behind this tragedy. Because it wasn't a single failure, was it? It seems like it was a dangerous chain of events that had its roots way back long before that fatal takeoff roll.
That's exactly right. We're going to explore how, fundamental errors in calculating key performance speeds were somehow overlooked, how engineers misinterpreted some basic aerodynamics, especially near the ground,
Okay.
how clear warning signs were missed or maybe dismissed, and crucially, how this overwhelming pressure from management to meet an unrealistic deadline ultimately created the environment where this disaster became almost inevitable.
Yeah. If you, like us, approach aviation safety thinking it's this fortress of redundancy and rigor, well, this deep dive is going to show you just how critical and sometimes how precarious that whole process can be.
It really can.
And what's fascinating is how the lessons learned here, they apply far beyond just the world of flight testing. Okay, let's unpack this.
Right. So the aircraft at the center of this story is the Gulfstream G650. It was announced back in 2008. Gulfstream's new flagship, bigger, faster, more capable than anything they'd built before. A huge undertaking for the company.
And a massive selling point, right?
Yeah.
A key promise they made to potential customers was the ability for this jet to operate from runways as short as 6,000 feet.
Which is pretty short for a jet this size.
Exactly. It significantly increased the number of private airports wealthy buyers could use, made the plane incredibly attractive, in the market.
But delivering on that 6,000-foot promise, legally, required incredibly precise and complex performance calculations, particularly the minimum takeoff distance needed if an engine failed during takeoff.
Okay, so to really understand what went wrong here, we need to quickly define a few key speeds. These are crucial for takeoff performance.
Yeah, let's break those down.
First up is V1, the decision speed. You can think of this as like the last moment a pilot can decide to abort the takeoff and still have enough runway left to stop safely.
Go, no-go point, essentially.
Right. Then there's V2, the takeoff safety speed. Now, this one is the absolute minimum speed the aircraft has to reach by 35 feet above the ground if an engine fails just before V1.
It's the critical speed that ensures you have safe control, safe climb performance on just one engine. And for the G650's design, meeting that requirement, hitting V2 by 35 feet after an engine failure, that was the performance limit. It dictated the minimum legal takeoff distance.
So Gulfstream needed this V2 value to be quite low to hit their 6,000-foot runway target.
Exactly. And there's one more related speed, VMU, or minimum unstick speed. This is determined experimentally, out in testing. It's the slowest speed the aircraft can physically lift off the ground, with the nose pitched up as high as possible without scraping the tail.
Okay.
And typically, the minimum V2 speed is derived using a formula based on this experimental VMU data. They're linked.
Got it.
Now, here's where the first really critical problem emerged. There was a regulatory change way back in the 1990s that altered how the minimum V2 was defined.
How so?
It changed from being 1.2 times the stall speed to 1.13 times something called VSR, which is basically the speed where the wings are supporting the plane's weight in a specific configuration. A subtle but important difference.
Okay, a new rule. So Gulfstream's engineers, working on the new G650, they decided to define their target V2 using this new regulatory minimum at 1.13 VSR.
Right, but here's the catch. They'd essentially used a similar calculation method aiming for the regulatory minimum for their older aircraft, like the J550, but under the old rule. So they were sort of carrying forward a methodology.
Okay.
And the crucial error was an assumption, a really big assumption. They assumed without actually performing the necessary checks against the G650's own experimental VMU data they assumed the G650 would behave like their older planes.
So they thought the real V2 speed, the one based on how the G650 actually performed in tests, would just naturally end up being lower than that regulatory minimum target they'd set.
Exactly. They just expected it to work out like it had before on different planes. And they didn't check that assumption against the actual G650 test data.
Wow.
And had they performed that check, crunch the numbers using the G650's real VMU data, they would have discovered something absolutely fundamental.
What?
The real V2 speed for this aircraft, the G650, based on how it actually lifted off the ground, it was inherently higher than that 1.33 VSR regulatory minimum they were aiming for.
That was impossible.
Aerodynamically impossible for this aircraft to safely achieve the V2 speed they had set as their goal.
That creates an immediate conflict, doesn't it? Because an achievable V2, which would have to be higher, that directly increases the minimum legal takeoff distance required for certification.
Yep.
And that higher distance would break the 6,000-foot runway promise made to customers.
Exactly. It puts them in a bind.
So instead of revising the target V2 to a safe, achievable speed, the logical engineering step, the decision was effectively made to task the test pilots with trying to figure out some way, anyway, to hit that unrealistically low V2 target, that 1.13 VSR.
Right. They were pushing the test team to achieve an impossible performance target. That really set the stage. But there was a second major technical problem just compounding the situation.
Yeah.
A fundamental misunderstanding of how the wings would behave when stalling close to the ground.
Okay. So during those early VMU flight tests, this was late 2010, before the fatal crash, there was a really telling incident, wasn't there?
Yes, there was. The pilot rotated the nose up a bit too much during one test, and the right wing just dropped. Suddenly, uncontrollably.
What did they make of that at the time?
Well, the source material says the test team discussed it, but it sounds like it was pretty informal. They kind of chalked it up to maybe pilot technique or perhaps some minor lateral instability issue.
But it was more serious than that.
Much more serious. What they didn't fully recognize then was that this wasn't just instability. The wing had actually stalled.
But why did it happen at a lower pitch angle than they expected?
That's due to something called ground effect.
Okay, ground effect. That's when you're flying really close to the surface, right? How does that change things aerodynamically?
Precisely. When an aircraft is within roughly one wingspan of the ground, the airflow patterns change significantly. The air hitting the underside of the wing can't easily flow down and away like it does higher up.
Okay.
This generally leads to increased lift and reduced drag at a given angle of attack, which sounds good. But critically, it also decreases the angle of attack, the AOA, at which the wing will stall. The critical angle where the wing stops producing lift properly is lower near the ground than it is higher up in free air.
And Gulfstream's engineers,
Yeah.
they underestimated this effect on the stalling.
They did. The sources say they relied on some academic papers that were, well, apparently flawed. These papers stated that the maximum lift a wing could produce was the same in ground effect as in free air.
Which isn't true.
Which, for many modern wing designs like the G650s, just isn't true. The actual maximum lift is often achieved at a lower angle of attack in ground effect, meaning the stall happens earlier at a lower pitch attitude.
Okay, so based on their incorrect calculations and using these faulty sources, they significantly overestimated the angle of attack where the G650's wing would stall in ground effect.
Exactly. They believed the stall AOA near the ground was around 13.1 degrees. But the reality, as testing later tragically confirmed, was that it could stall at an AOA as low as 11.2 degrees.
That's a big difference when you're talking about takeoff.
Huge difference. And it has major implications for safety systems.
Right, so when they calibrated the stall warning systems, things like the stick shaker, which violently shakes the controls to warn the pilot, and the pitch limit indicator on the display, they set those based on that incorrect belief.
Yes. The warnings were set to activate at 12.3 degrees AOA when in ground effect.
Okay, I see the problem. This creates a really dangerous gap.
A critical gap. Because the real ground effect stall AOA could be as low as 11.2 degrees, but the warning system wouldn't activate until 12.3 degrees.
Meaning you could actually enter a stall before getting any warning from the aircraft.
Precisely. That earlier wing drop incident, that was a clear, flashing warning sign of this exact unwarned stall condition. But it wasn't properly understood or acted upon at the time.
So you've got the situation. The test team is trying to achieve an impossible V2 speed. The plane's wing can stall earlier than they think it can near the ground, and potentially with no warning.
Yeah.
It really feels like they were heading towards a cliff edge without even realizing how close they were getting.
Absolutely. And in the weeks leading up to the crash, this was early 2011, the test team was really struggling. They were just repeatedly overshooting that low target V2 speed during the takeoff performance test.
They were trying to find a technique, basically, to make the plane do something it wasn't designed to do at that speed.
Essentially, yes. The source material describes this rather unusual, almost jerky technique they experimented with back in February 2011.
How did that work?
Well, they'd rotate the nose up quite high initially, then try to actively hold the pitch angle lower during the ground roll, specifically trying to stay below that 11-12 degree AOA zone where they thought the danger for roll issues was.
The issues they hadn't identified as stalls yet.
Right. And then after liftoff, they'd abruptly pull up quite steeply.
Why do that?
The logic, it seems, was to avoid those roll issues they'd seen at higher AOA during the ground run. Then once airborne, they'd execute that sharp pitch up, hoping to shed speed quickly and somehow get down to that low target V2 by the 35-foot mark.
Did it work? Did they hit the target?
They did manage to get closer. The sources say within 4 knots of the target V2 using this method on some runs, but it wasn't consistent, and critically, it didn't meet the strict test parameters, which usually require hitting speeds within plus or minus 2 knots.
And more importantly,
the pilots themselves felt it was completely unnatural. It wasn't a technique that regular civilian pilots could ever be expected to use safely in a real-world situation, nor was it something the FAA was likely to approve for certification.
So there was frustration building.
Definitely. And this frustration really came to a head on the morning of April 2nd, the day of the crash. Test pilot Kent Crenshaw, the pilot in command for that flight, expressed his strong feeling that this jerk stuff, as he called it, just wasn't working. It wasn't how the aircraft should be flown.
He made a good point, didn't he? About real emergencies.
A critical point. He emphasized that in a real emergency, pilots wouldn't be focused on hitting some precise, tricky pitch angle. Their absolute focus would be on achieving V2, whatever it took, to ensure a safe climb out.
So, based on that conversation, the crew decided to try a different approach for their test runs that day.
Yes. Instead of that aggressive, jerky technique, they planned to attempt a smoother, more continuous pitch-up maneuver during rotation.
How would that work?
The idea was to try gradually holding the nose lower for shorter durations on the ground in successive test runs. They were essentially searching for this non-existent sweet spot, a smooth rotation that would somehow avoid the roll issues they'd seen, but still magically allow them to hit that impossible low target V2.
They were still chasing the impossible target, just trying a different way.
Exactly. And that brings us directly to the fatal Flight 153. It was designated Test Run 7A2. The plan was a simulation of an engine failure right at V1, with the flaps set to 10 degrees, a pretty standard test configuration.
And the crew.
Captain Kent Crenshaw was pilot in command, First Officer Vivan Ragusa was SIC, along with the first flight test engineer, and David McCollum, another engineer. Ground engineers were monitoring telemetry from a trailer nearby.
Okay, so the takeoff roll began normally. As they reached 105 knots, First Officer Ragusa called CHOP, simulating the engine failure by pulling back the power on the right engine.
Correct. They continued to accelerate on the remaining engine, and then Ragusa called rotate, the command for Captain Crenshaw to pull back on the controls and lift the nose.
And Crenshaw responded smoothly, pulling back. The pitch angle started to increase, going past 9 degrees.
And this is where the culmination of all those problems we discussed just unfolded in mere seconds. It happened incredibly fast.
Not fast.
Just 4.4 seconds after the rotation began, while the plane was still physically on the runway, the angle of attack reached 11 degrees. Now remember, this is still below the incorrect warning threshold of 12.3 degrees.
But right at the edge of the real ground effect stall, AOA.
Precisely. A fraction of a second later, the aircraft lifted off the ground, and just 0.2 of a second after becoming airborne, the angle of attack hit 11.2 degrees.
The stall point.
The exact lower limit of the real ground effect stall angle. At that precise moment, the right wing stalled. And crucially, there was no prior warning from the stick shaker or the pitch limit indicator because they were calibrated based on the wrong data.
The plane immediately rolled violently to the right. Captain Crenshaw instinctively reacted, applying left aileron input to try and counteract the roll.
But with the right wing fully stalled, the ailerons were basically ineffective. They couldn't control the roll. He exclaimed, something is going on. You can hear the surprise and confusion.
And the stick shaker finally activated.
Yes, but far too late. The stall was already developed. Now believing he was near the stall angle indicated by the now active warnings, and relying on the pitch limit indicator's faulty information about where the stall should be.
You push forward.
Crenshaw pushed the controls forward slightly, attempting to pitch the nose down to recover from what he thought was an impending stall based on the warnings he just received.
But the stall had already happened at a lower angle.
Exactly. So pitching down slightly wasn't enough to fix the fully developed stall on the right wing. With the plane banked about 13 degrees right and still descending slightly toward the runway, the right wingtip actually struck the runway surface, scraping along.
Oh, man. You can imagine the alarms going off.
First Officer Ragusa cried out, and the automated system started shouting, "Bank angle! Bank angle!"
What did Crenshaw do then?
In desperation, he yelled, "Power, power, power!" And Ragusa slammed the power levers to full, even on the simulated failed engine, trying to arrest the descent. But the plane's bank angle just kept increasing to the right.
He must have been completely confused why pitching down hadn't worked.
It seems so. Still unsure why the initial pitch down didn't fix it, and possibly thinking he just needed to get airborne, regain altitude, Captain Crenshaw then pulled the controls back hard again, trying to climb away.
And that was
the final fatal maneuver. The angle of attack shot up dramatically, way past 22 degrees, far, far beyond any possibility of recovery from the stall. The right bank angle increased incredibly rapidly.
You heard Ragusa again.
Yeah, First Officer Ragusa's voice rose in panic, "No, no, no, no!" Followed again by the automated bang angle. Warning. Captain Crenshaw's last words, just a tragic acceptance of the inevitable, were, sorry guys.
Oh, heartbreaking.
Just 15 seconds after lifting off the ground, the right wing hit the ground hard again. The aircraft spun off the side of the runway. The fuselage slammed down hard, sliding on its belly across the rough desert ground.
And it hit something.
It hit a small concrete structure, likely an instrument landing system support. That impact ruptured the fuel tanks in the wings. There was an immediate, massive explosion, and the aircraft came to rest completely engulfed in intense flames.
The source material mentions the impact itself might have been survivable.
It indicates that, yes. Apparently, Captain Crenshaw was pinned by the wreckage, but the other 3 crew members managed to unstrap themselves. They were trying desperately to open the main cabin door to escape.
But the fire.
The fire was just immediate and incredibly intense. The ground test team, they were in a trailer nearby. They saw the crash and ran towards the burning aircraft, but the heat was just too much. They couldn't get close.
And the airport fire trucks.
They arrived quickly, within about 4 minutes, according to the report, but by then, tragically, there was just no chance for survival. The fire was too overwhelming.
It's such a tragedy. The NTSB obviously launched a full-scale investigation.
They did, and it was complex. Partly because, thankfully, flight test accidents like this are relatively rare. They ended up relying heavily on the surviving members of the Gulfstream test team to understand the context, the procedures, the events leading up to it.
And their technical findings, did they confirm what we've been discussing?
Absolutely. They confirmed the whole chain. The outdated procedure used to calculate that target V2, resulting in a speed that was aerodynamically impossible to achieve safely. They confirmed the incorrect assumption about the wing stall, AOA, and ground effect, and they traced that back to relying on those flawed academic sources.
And the warnings.
Confirmed that the stall warning systems were incorrectly calibrated based on that flawed AOA data, meaning, yes, a stall could occur with no pilot warning. The NTSB concluded the crew was essentially tasked with an impossible goal. They attempted a maneuver that inadvertently pushed them right to the aircraft's stall limit without any warning, and they just couldn't recover in time with the faulty information available to them from the plane's systems.
So Crenshaw's initial pitch-down attempt, it was logical based on the bad data he was seeing.
Exactly. It was the standard recovery technique, but it was based on the erroneous stall AOA displayed by the plane's instruments, which didn't reflect the reality of what the wing was doing.
But the NTSB didn't just stop at the technical side, did they? They really dug into the organizational and managerial factors at Gulfstream.
They went much deeper. They identified several critical organizational issues that really contributed to setting the stage for this crash.
Like what?
Well, for instance, those 2 previous uncommanded roll incidents during the earlier VMU testing, the ones that were clear indicators of this ground effect stall problem, they weren't properly investigated.
How so?
It sounds like they were just discussed informally, kind of brushed off, attributed to pilot technique perhaps. There was no formal process in place, it seems, to actually halt testing and conduct a thorough analysis when a significant, unexpected event like that occurred.
That seems like a major oversight in flight testing.
It is. There was also that fundamental failure we talked about earlier, not verifying the calculated target speeds against the actual experimental VMU data they had already gathered.
Still assuming the new G650 would perform just like the old G550.
Right. Even though apparently some simple cross-checks would have shown glaring inconsistencies, like the fact that the liftoff speed derived from their target V2 was actually lower than the plane's minimum unstick speed, the VMU, which is physically impossible. Basic validation steps were just skipped.
And they mentioned something about control gates.
Yes. The NTSB highlighted a lack of clear control gates in Gulfstream's development process. There wasn't a required formal step to complete the full analysis of that critical experimental VMU data and officially sign off on the speed schedule before moving ahead to the next phase, the takeoff performance testing.
So they proceeded without fully understanding the basics.
They proceeded with a dangerous lack of fundamental knowledge about the aircraft's low-speed handling qualities right near the ground.
Were there issues with the team structure too?
It seems so. Duties weren't always clearly defined or perhaps resorted adequately. The first flight test engineer, for example, reportedly had a massive workload responsible for both supervising these complex, high-risk tests and performing the critical analysis of the VMU data from previous tests.
It sounds like too much for one person.
And that crucial VMU data analysis wasn't even finished when management was already pressuring the team to start the next phase of testing, the takeoff performance runs.
Which brings us to the big one.
Exactly. This brings us to what the NTSB identified as the most significant underlying factor, the root cause that really allowed all these technical and procedural failures to line up and lead to disaster, schedule pressure.
They found management pushed too hard.
The investigation found that right from the very beginning of the G650 program, Gulfstream management pushed for what the NTSB called an overly aggressive, even unreasonable schedule.
Why? What was the rush?
The primary driver was a specific looming deadline, September 28, 2011. That date marked the 5-year anniversary of the aircraft's formal type certificate application with the FAA.
And that date was important because...
Because meeting that date would allow Gulfstream to certify the G650 under the existing regulations. If they missed it, costly new airworthiness regulations would come into effect, adding significant expense and delay to the program.
So it was about avoiding new rules and costs.
Very much so. The corporate focus became intensely fixed on meeting that September deadline. Missing it meant delays, dealing with those new regs, and ultimately losing significant money. The sources are quite blunt about it. In this context, they state that money is king.
Did people raise concerns about the schedule?
Yes. Management apparently knowingly accepted risks and maintained that aggressive schedule even against warnings from within their own engineering team. People pointed out that the timeline didn't allow for necessary contingencies or dealing with unexpected issues found during testing.
But management pushed on.
The director of flight sciences explicitly stated he wanted to maintain a sense of urgency, even acknowledging that the schedule was likely unattainable. The pressure was immense.
Even the FAA was worried, weren't they?
Yeah, they were. The FAA actually sent Gulfstream a formal letter in March 2011, just weeks before the crash, expressing concerns about the unrealistic schedule they were pursuing.
What happened with that?
Well, the FAA didn't really have the regulatory teeth to force Gulfstream to slow down before the formal certification flight testing phase began. And tragically, the crash happened before Gulfstream even had a chance to formally respond to the FAA's letter of concern.
So this intense schedule pressure just permeated everything.
It really seems like it. It created an environment where cutting corners, like using outdated calculation methods from previous aircraft, became acceptable because it was faster. It meant early warning signs like those uncommanded rolls weren't rigorously investigated because stopping testing would cause delays.
And it kept the focus on the target, not the reality.
Precisely. It led the entire team to become fixated on achieving the goal that unrealistically low V2 speed needed for the crucial 6,000-foot runway promise, instead of stepping back and questioning if that goal was even achievable or, more importantly, safe, given the aircraft's fundamental aerodynamic characteristics.
So increasing V2, the obvious technical solution to the performance problem.
That was essentially off the table. It wasn't seriously considered because it would shatter the schedule and break those critical customer promises tied to the deadline.
It took this terrible accident then for Gulfstream to really step back and make fundamental changes.
Yes. They immediately halted all G650 field testing for several months after the crash, a complete stop.
What changed when they restarted?
They developed completely new, sophisticated computer models. These were designed to really understand the aircraft's complex behavior, especially near the ground, and to develop safe flight techniques and accurately assess stall margins before trying things out in the actual plane, moving away from that risky trial and error approach in the air.
And the V2 speed.
Crucially, they abandoned that impossible target V2. They increased the G650's certified V2 speed by a full 15 knots, bringing it up to a safe, achievable speed based on the aircraft's actual performance.
But what about this 6,000-foot runway promise?
They were still able to meet that 6,000-foot runway promise to customers eventually, but they achieved it the right way, not by forcing the plane to operate unsafely at a speed below its capabilities, but by increasing the engine thrust slightly. They found a safe engineering solution.
They also improved their processes.
Significantly. They put in place much better tools for detecting anomalies in flight test data, and they created robust, mandatory procedures for immediately stopping testing and thoroughly investigating any unexpected events, completely unlike the informal approach taken before the crash.
Any changes to the plane itself or procedures?
Yes, they even modified the physical aircraft design somewhat, adding things like more effective fire suppression systems and additional emergency exits. And they instituted a new safety policy, having airport firefighters on standby right at the airfield for all high-risk test maneuvers.
So the G650 was eventually certified.
It was, on September 7, 2012, nearly a full year later than that original aggressive deadline they were chasing. And despite the delay and the tragedy, the G650 went on to become a very significant commercial success for Gulfstream.
But that delay and the 4 lives lost.
It's hard not to conclude they were a direct consequence of prioritizing that unrealistic schedule and those corporate goals over a rigorous engineering process, over basic safety due diligence. The technically correct path was available earlier.
So when we look back at this whole deep dive, what are the really core takeaways here beyond just the specific technical failures?
Well, the technical failures, the V2 calculation error, the ground effect misunderstanding, the warning system calibration, those were the immediate cause of the crash, no doubt. But the NTSB's findings make it abundantly clear, I think, that the root cause was organizational and managerial.
The pilots were put in an impossible spot.
Exactly. They were put in an impossible situation because flawed data and truly unrealistic expectations were allowed to persist and compound. And this was largely driven by that intense corporate pressure to meet a specific, financially motivated deadline.
And this story, it's rooted in highly technical aviation, obviously, but the lessons seem much broader, don't they?
Oh, absolutely. The dangers of relentless schedule pressure, the failure to question fundamental assumptions, the tendency to ignore or explain away early warning signs, allowing corporate targets to override safety concerns or proper process rigor.
Yeah.
These aren't unique to building airplanes.
No.
You see these dynamics playing out in project management and decision-making in almost every industry you can think of. Software development, construction, finance, medicine. The list goes on.
It's a powerful reminder, isn't it, that even in fields absolutely designed for safety, like aviation, the human and organizational dynamics can create conditions where disaster is still possible.
It truly is. Gulfstream, to their credit, made significant changes after this tragedy. They learned incredibly hard lessons, paid a terrible price.
But here's maybe a final thought for you, the listener, to consider. This incident was a devastating wake-up call for one specific company. But the question is, will managers and leaders in other companies across other industries truly internalize the lessons from this story? Or will a constant pursuit of speed, of market share, of the bottom line, continue to push teams past safe limits, continue to risk well-being, and sometimes even lives for, the almighty dollar?
Yeah.
It's a question that extends far, far beyond the cockpit of a business jet.